So in this lecture, I want to talk about some kind of, I want to say, more advanced topics. The first topic is going to be graphs. These graphs are not graphs in the usual sense that we're familiar with, graphs from calculus or algebra. This is not that. So here, a graph would just be, I have a set of vertices and I have a set of edges. Right? So there's a graph. I have 5 vertices, and among those vertices I have edges. So here I have, between this pair of vertices, I have 2 distinct edges. Right? I might also have a loop, right? I'm gonna have a kind of an edge with itself. That doesn't come up as often because it's rarely useful, but it's possible. And these also might be weighted edges, so I could think about these vertices as being cities, and the edges between them are roads. And the roads might be different lengths, and I might want to say, how do I find a minimum distance path from one place to another? I could also, so I could say like a 5 and a 7 and a 3, and those might be distances, and I'd like to know, I haven't labeled all of the edges, which I would need to, but I might, pick 2 points and want to know what's the shortest path between the two. Or these 7 and the 5 and the 3 might actually be not actual distance, but travel time, and I would want to know the fastest path. And in fact, solving problems like this is a lot about how your GPS on your phone that constantly updates to take into account like traffic and things like that. They operate by solving optimization problems like this. And if you want things that work in real time like that, they have to be able to update very quickly. So computationally, you'd like to be able to solve like shortest path problems very quickly. I could also spice the problem up a little bit by making some of these things like one-way roads, right? So here I put some arrows on some of these roads. So anything that doesn't have an arrow, I'm going to assume it's two-way, but the things with arrows are one-way. So that kind of makes the problem slightly more difficult by saying some of these are only one-way roads. So it kind of limits my options a little bit. So this is a graph. It's used to model. So we already gave a specific example of actual cities and roads and paths and minimizing travel time or transportation cost. Another application would be modeling like networks and connectivity. Right? So I could say, these people are related and these people are related, and I have a strong interconnection over here where I have vertices or people, and edges between them are relationships, and I could have clusters and things like that, and you want to do analysis. And so a lot of times, so if you're talking about networks, if you have like a set of computer networks, you'd like to know that we have uninterrupted communication, right? Or if I have a big group of cities over here, I might have many roads over here between these cities, right? And then a group of cities over here, and many roads over here, and then one road from here to here. This is not necessarily a great setup, because if we have an accident on this road and that edge is now gone, I don't have any way to get from over here to over here. So what we'd like is to have a pretty good connection between any 2 sets of vertices. And so kind of you look at like sparse cut problems, you look at the min cut problems. So a lot of things in graph theory that have to do with kind of what is the most cost, because we assume that every edge that we put in here, right, if it's a road, that costs money. So every edge that we put in here represents some additional cost. So we can't just go around throwing edges as if we have no budget. We'd like to know, if we have some budget for edges, how do we put them in such a way to kind of make the separation, to break the connection, basically. If I have this group over here, this group over here, and then just one road, that's a very weak connection. It's very easily broken. I only need one accident to get that. But if I have at least 3 roads from this group to this group, then I'm going to have to take away at least these 3 roads. And I need 3 simultaneous accidents to block these cities from these cities. And 3 simultaneous accidents is much less likely than 1. Okay, so you have kind of sparsity problems like this, and a lot of what you might find yourself doing is optimization problem that has to do with transportation costs and sparsity and things like this. So one thing mathematically that we like to talk about with graphs, so I'm going to ignore the directional parts. So here I put some arrows on some of these, and I said this is a directional path, right? I can only travel in the direction of the arrow. I'm not allowed to travel the other way. So a graph with directions on it is called a digraph for directed graph. Any graph that doesn't have arrows is just called a regular, or it's just called a graph. I'm just going to talk about graphs here, not directed graphs, although you can You can change things up a little bit, adapt what I'm about to say to take care of directed graphs, but just to keep things simple, I'm going to talk about regular graphs. You can also weight the edges, so we have like transportation costs or travel time here on the edges. I'm going to ignore problems like that and just focus on one simple type of problem here. So, if you've ever seen Good Will Hunting, and you know that Will, in Good Will Hunting, he solved a problem and he wrote a solution on the board, and the first problem that he solved had to do with graphs and adjacency matrices. So what I'm going to say is if I have a graph, right, so I'm going to put some edges here, and I'm going to label my vertices. Okay? This is a simple graph. A simple graph is a formally defined term. It means I don't have multiple edges between any pair of vertices. So if I look at any pair of vertices, I have either 0 or 1 edge between the two, and I don't have any loops, right? So that's a simple graph, and I'm going to make a 4x4 matrix. I'm going to make a 4x4 matrix because I have 4 vertices, right? So I'm going to go look at the row I, column j entry of this matrix, and that row I, column j entry of the matrix is going to be a 1 if vertex I and vertex j are connected by an edge here, and 0 if they're not. So I look at 1, there's no loops. 1 is not connected to itself by any vertices, so I'll put a 0 here in the 1, 1 spot because 1 is not connected to 1. Same reason on 2, there are no loops, so 1 is not connected to 1, 2 is not connected to 2, 3 is not connected to 3, 4 is not connected to 4, so the row 1, column 1 entry is 0, row 2, column 2 entry is 0. So look at vertex 1 and 2, there is an edge between those, so in row 1, column 2, I put a 1. This is an undirected graph, so if there's an edge between 1 and 2, there's also an edge between 2 and 1, so that 1 there means there also has to be 1 here. I look at 1 and 3, there's an edge, so I put a 1 here in row 1, column 3, also row 3, column 1. There's an edge between 1 and 4. So these 1s are telling, so this top row is telling me that the vertex 1 is not connected to itself by any loops, but it is connected to 2, 3, and 4. That's what those 1s are telling me. So look at 2 and 3. So the next thing that I don't know is in row 2, column 3. I look at 2 and 3. They are not connected, so I put a 0 here and here. I look at 3 and 4. 3 and 4 are connected, so row 3, column 4, I put a 1 because 3 and 4 are connected. And then I have what am I looking at? 3 and 4. I'm sorry. 2 and 4. I messed up. So 2 and 4 are not connected. Row 2, column 4. And then 3 and 4 are connected. So this is the adjacency matrix for this graph. I'm going to call it A for adjacency. And this almost miraculous property of adjacency matrices is, I'll say now, I can interpret this as the entry in row I, column j, tells me how many paths of length 1 there are from vertex I to vertex j. Okay? So look in row 1, column 2, there's a 1 there. That tells me there's 1 path from vertex 1 to vertex 2 of length 1. It's at that 1 edge. When I say length, I mean the number of edges involved in the path. So there's 1 path of length 1 from vertex 1 to 2. Okay? And 2 and 3, right? So row 2, column 3, there's a 0 there. It's because there's 0 paths of length 1 from 2 to 3. Now I might want to say, how many length 2 paths are there? How many length 3, 4, 5, 6 paths are there? And so, almost magic property of adjacency matrices is if I take this matrix and raise it to the power n, I'm going to get some matrix here. And if we diagonalize the matrix like we did with the Fibonacci matrix a few lectures ago, we can very efficiently raise this matrix to a high power. Okay? So I want to raise this matrix to a high power. And if I raise it to the power n, and I look in row I, column j of a to the power n, that's going to tell me how many distinct paths there are of length n from vertex I to vertex j. So for example, I said, how many paths are there of length 2 from vertex 2 to vertex 3? There should just be 1. I can go from 2 to 1 and then from 1 to 3. That's a path of length 2 and that's it. Right? So I want to know what is the entry in a squared. So a to the power 2 is going to tell me about paths of length 2. And I want to know what is in the row 2, column 3 entry of this matrix. So I'm going to take, remember how matrix multiplication works. So 0, 1, 1, 1, 1, 0, 0, 0. Okay. So I'm going to take row 2 here and multiply by column 3 over here. So I have 1 times 1, 0 times 0, 0 times 0, and 0 times 1. So I just get a 1. So in row 2, column 3, I'm going to have a 1 here, and that 1 is that 1 in row 2, column 3. Okay. Because this is in row 2, column 3, it's telling me about paths from vertex 2 to vertex 3. And because this is second power, it's telling me how many paths of length 2 there are. Okay. So, and we got 1, just like we said we would. So, at first it might seem like magic, but if you think about it for a moment, about why matrix multiplication actually works this way, and why does raising this matrix to powers tell me about this matrix, the adjacency matrix, if I square it, why is this telling me about paths of length 2? I encourage you to think about that, because it'll probably dawn on you and make perfect sense. Something similar to this is Markov processes. So a Markov process, so hopefully you're going to see a lot of probability and statistics in your future, because those are beautiful and very useful subjects. So a Markov process is a stochastic process, which basically just means one that evolves over time. So I have some, I'm going to say, random variables, x1, x2, x3, x1, x2, x3. I'm going to think about the 1 and the 2 and the 3 as being time, right? And x1 is a random variable, which means it doesn't have a specific value. It assumes different values with different probabilities. x2 assumes different values with different probabilities. And so x1, x2, x3 could be, for example, so you have a washing machine, right? x1, x2, x3. x1 could be the state of the washing machine on day 1. x2 could be the state of the washing machine on day 2. x3 could be the state of the washing machine on day 3, etc. And so the washing machine could either be broken or fixed. So broken could be 0 and fixed could be 1. Right? And so it could be in either one of those states. And I might have some knowledge about, well, if I know what state the washing machine is in today, then I have probabilities for what it's going to do tomorrow. So the probability that it's broken tomorrow, given that it's broken today, is, let's go ahead and make something up, 0.25. Okay. And the probability that it is broken tomorrow, given that it is fixed today or working today, is, let's say, 0.5. Okay. I'm claiming that this is enough information for you to figure out everything else. So if it's broken today, then the probability that it's broken tomorrow is 0.25, which means the probability that it's not broken tomorrow is 0.75. If it's fixed today, the probability that it's fixed tomorrow is also 0.5. Those are the only two options. Right? So what I can do here is say broken equals 0, fixed equals 1. Okay. So I probably should have done 1 and 2, so let's say 1 and 2. It's going to make things easier for the rows. So broken being 1 is going to correspond to column 1 and row 1, and fixed being value 2 is going to correspond to row 2, column 2. So I'm going to look over here in the 1, 1 position. So 1 corresponds to broken, so 1, 1 is going to be the probability that it's broken tomorrow, given that it's broken today. So broken corresponds to 1, so 1, 1 means broken, broken. Broken tomorrow, broken today. So that is 0.25. Okay. So broken is 1, probably that's broken tomorrow, given that it's broken today, is 0.25. Okay. So now, I'm going to say over here, the probability that it is, this is row 1, column 2, this is going to be the probability that it's broken tomorrow, given that it's fixed today. That one is 0.5. So I don't necessarily have to do it this way, where I do these things in the first row. These could be in the first column, and it wouldn't change anything. But I'm reading row 1, column 1 is broken, broken. So row 1, column 2 is 1, 2. So it means 1 corresponds to broken and 2 corresponds to fixed. So that's the reason I'm doing things in this way. Because the first number, the row number, is telling me about what's happening tomorrow, and the second number is telling me what's happening today. And so over here I'm going to have 0.75. Probability that it's fixed tomorrow, given that it's broken today. Okay, it's just 1 minus this. Okay, and this one is going to be 0.5. And we have a lot like an adjacency matrix. This is called a transition matrix for Markov process. So Markov process, hopefully you'll read more about it later, but a Markov process is a process consisting of multiple random variables where if I know information about what's happening at a certain time, then I know the probability distributions for what's going to happen at later times, regardless of past information. So if I know what's happening today, I have a probability distribution for what's going to happen tomorrow, and it would not help me to know what happened yesterday. Right? So if I know what happened today, then I have my probability distribution for tomorrow, and additional information about yesterday would not help me. That's the essence of a Markov process. Right? So this is my transition matrix. I'm going to call it P. Okay. So this tells me transition probabilities for a single day. Right? So today and tomorrow. Right? Now if I do P squared, and I can look in the row 1, column 1 entry of P squared, that's going to tell me the probability that it's broken 2 days from now, given that it's broken today. I can look in row 1, column 2, that's going to tell me the probability that it's broken 2 days from now, given that it's fixed today. Okay. So raising this thing to powers, just like the adjacency matrix goes from single edges, length 1 paths, to higher length paths, this tells me about transitions from one day to multiple days. And the reason this works is because of Bayes' rule, and I highly recommend you write it out because it might seem like magic for why, p to the 10th power is telling me about transitions over a period of 10 days. But if you actually write it out, you're going to see exactly why it's true. So I recommend going through that computation yourself and seeing if you can figure it out.